No, this final is a bit harder. The practice is a bit harder. The practice is a bit harder. Now can you guys see me now? Oh, you can see me? Oh, okay, great. Oh, how much delay is there? How much delay between, like 20 seconds, maybe 10 seconds? Okay, great. Okay, great. Okay, everybody, can you guys hear me? Yeah, very good. Great. Okay, let's get started. Okay, the format will be the same. So we'll go through over the questions. So I mean, the structure will almost kind of be the same. So you have the 3 questions will be the propositions from the notes. And then, it's homework, some stuff, maybe new stuff. But I would say it's the actual final. Tomorrow's final is a bit simpler. I think it's simpler than this and definitely shorter. Okay? This is what I would say. Okay, so the first question. Everybody, you guys can hear me? The sound is echoing. Okay. Anyone else having the same issues with the sound? I can hear you well. Okay, great. Okay, so the first question. Exercise 1. Do I need to write the questions or I can just do it? Yeah, guys, I can just do the questions, right? I can just do the questions. I don't need to write them. Okay. Okay. So state the 3 Sylow theorems. Sylow's first. So first, let G be a finite group. And P. The beginning of erasing. And P be a prime numbers dividing G. Suppose that the size of G is equal to P to the K times N, the sum K N, and M and N such that P doesn't divide that. Or GCD PM is 1. I don't know what I wrote in class. GCD PM is 1. Okay, doesn't matter. Or GCD PM. Sylow's first. G has a subgroup. Order. Okay. Right? That's the first theorem. Everybody, we got this? Okay, great. That's 1 point. Second. If you call the Sylow P subgroup, a Sylow P. Okay. Cool. If H and K are Sylow P subgroups of G, then H and K are conjugate in G. Everybody, we got this? Everybody, we got this? We got these 2 questions? Okay. 3. Sylow third. the number NP of Sylow P subgroups of G satisfied NP is congruent to 1P and NP divides Are we good here? But what is S? Sure, yeah, you can say that. But what is S here? What is the point? So what you mean is that the okay, Victor, what is the point of this? I think you mean that the set of conjugates of P is equal to all the Sylow P subgroups, maybe. Okay, great. So this is good, right? 3 marks. 3. Okay. Now, this is part 1. I'll erase it. I'll try to keep the writing on this part of the board so that you can see. Okay? Great. Now, the second question asks you to show that if G is a group, find the group, and P a prime number dividing the size of G, then NP is congruent to 1P, where NP is the number of Sylow P subgroups. Okay, this is really from the nose, right? Great, this is a bit long, but I ask you parts of the proof. Okay, so let's do it. So let P, of course, you can assume the first and second Sylow theorems. Okay, so first, let P be a Sylow P subgroup of G. Why does it exist? By Sylow's first, right? And let P be a Sylow P subgroup of G. And let S be the set of conjugates of D. Then P acts on S in the following way. So you have a function from plus S to S that sends Y and X P X inverse to Y star X P X inverse, which is just Y X P X inverse Y inverse. Here Y is in P and X is in P. Okay, you don't need to show it's an action because this is not the point of the question. You don't need to rederive it. Okay. Now, what is that? If Y is in P, then what is Y star P? Is YP, Y inverse, which is equal to P. And P belongs to S clearly, right? So P, S is a fixed point of the action. Sorry. Now, what do I need? I will show that P is the only fixed point, right? Suppose P prime is a fixed point of star. We show that. Okay. Great. Can I erase here? Can I erase this part? Okay, I'll erase this part. I'll try to keep it here. We said P should be prime. Okay. Since P prime is a fixed point, then if Y belongs to P, then Y star P, then Y star P prime is equal to P prime, because P prime is a fixed point. Y P prime Y inverse is equal to P prime. Hence, Y belongs to the normalizer Ng of P prime, where Ng P prime is just the set of, say, G and G, such that G P prime P inverse equal to P prime. Okay, so now I understand these symbols, you don't have to define them if you use them the same way I use them in class. Okay? Therefore, since Y is an arbitrary element of P, since any arbitrary element of P belongs to NGP prime, then, therefore, P prime, therefore P is a subset of NGP prime. So P is a subgroup of NGP prime. Right? Those are. Hence, P prime, it's P and P prime are subgroups of NGP prime. Right? Because P prime is already a subgroup of P prime. Now notice, what do I know about NGP prime? It's also a subgroup of G. So if you want, you can write this P prime are subgroups of NGP prime, which is a subgroup of G. Right? The orders, hence the orders divide each other. Right? Hence, P to the K divides the size of NGP prime, which divides P to the K times N by Lagrange. Now, how can I then write NGP prime? What is the size of NGP prime? How many powers of P does the size of NGP prime contains? If this one has K, if P here, P divides this one exactly K times, and P divides this one exactly K times. And this is in the middle. How many primes does NGP prime contain? How many K? Yes, how many P? K. Hence, NGP prime is equal to P to the K, let's say, times T, where DCD, if it is 1, T is in N, of course, Therefore, PP prime are Sylow P subgroups of NGP prime, and hence must be conjugate what theorem is that? Sylow's second theorem. Very good. And hence must be conjugate in NGP prime. So there exists, let's say, x in NGP prime such that x p prime x inverse is equal to p. Now, if x is an NGP prime, what is x p prime x inverse? If x normalizes p prime, is p. Exactly. This is p prime. So how many fixed points do I have in that case? I have exactly one fixed point. And star has exactly one fixed point. And P is the only fixed point of star. And what theorem do I use here? Why does NP is congruent to N not P? Yeah, so if you have a P group acting on a finite set, right? The cardinality of the set is congruent to the number of fixed points mod P. Hence, a star has only one fixed. Now, S, P is a P group, P is a finite P group. And S is a finite P set. Hence, the size of S is congruent to the number of fixed points of star on P. This is congruent to 1 mod P. Now, the size of S, what is the size of S is the number of conjugates of P. Why is it equal to the number of Sylow P subgroups of P? Why is that? Why is the size of S congruent to 1 mod P? Why is size of S is equal to NP? By Sylow's? Second, because the number of conjugates of S is equal to the number of Sylow P subgroups. Okay? Okay. Okay, so this is quite a bit long. So this was a bit long. But okay, the other ones are shorter. Great. I mean, expect the final tomorrow to be shorter than this. Okay? Tomorrow is going to be shorter than that. Okay, so if you're comfortable with this, you're comfortable with the speed and everything, then you should be. Okay, great. Now, exercise 2. Let R be a ring. Define the unique ring homomorphism R let n be bigger or equal to 2. And suppose that one R has additive order n and R plus. Show that per phi is equal to nz. Show that every element in R has additive order dividing n. Okay, let's prove this. One. So if curve phi is equal to nz, what do I need to show? So n belongs to curve phi. If and only if what? If and only if m times 1r is equal to 0r, right? Everybody, is that right? If and only if the order of 1r divides m, right? Right? The order of 1r divides m. Divides n. Since 1r has finite order, divides m. If and only if n divides m. If and only if m belongs to n. What is the kernel? Curve phi is okay. Is that what you're doing class? I did this in class, okay. But this was done in class, I think. Okay. Is that how we did it in class? Oh, okay. What did I do? Oh, okay, okay. But it's the same. Like it goes up and down, the same idea, right? Yes. Okay. Yes. Yes. Okay. So first I said that curve phi is an ideal, so that curve phi is the form something. Okay. Yeah, but I mean, I think that is right. That's right. This is right. This looks right. M belongs to curve phi. Only if, yeah. Okay. Great. Now show that every element in X has additive order dividing n. So let X be an R. X plus X n times is equal to X times 1R plus 1R n times. Right? Now what is the additive order of 1R? And so what is 1R plus 1R n times? 0. Hence, any X R has finite additive order divided by. That's it. Oh, okay, okay, yeah. Yeah, Victor. Yeah, the exam is well. I don't think they're yeah. The in betweens are sparse and the extremes. Okay. Yeah, because phi of m will be 0 if m is in curve phi, right? And this is phi of m. This is the definition of the unique homomorphism, right? Yeah. I mean, you don't have to redefine these, okay? If I give you a unique homomorphism, you can assume its formula, you can assume everything. Okay? So this is 10 points. You see that this is easier than the first part. It's less long than the first part. It's way shorter than the first part, no? And it's the same amount of points. Okay? Any questions, people? Any? Okay. Great. X3. Let R. Yeah, finite. Oh, yeah, commuter rank. And A be different than 0R. Being R. Let F from R to R since X greater than X. Now this is a proof we did many times. The injectivity pairs we did many times, but we never stated it this way, right? We never stated it, but this is a part of the theorem. So I can read it tomorrow. I can ask you show that if A is not a zero divisor, then F is injected for you without everything. Okay, for sure. That if A is not a zero divisor, then F is injected. Let R show that if R is finite, and A is not a zero divisor, A is a unit. Of course, if you don't get the first question, you can move on to the second question. Okay, you can still do the second question, assuming the result of the first. Okay, was this okay? Was this question okay? This is the notes. So suppose A is not a zero divisor. And let x1 be an R such that fx is equal to f1. Then ax is equal to a1. So a times x times y is equal to 0R. Right? Now, really, what you can do it another way, but I don't think I did this way in class. You can see that F is a group homomorphism from R to R. And then it would be injected if an okay. Did I do it this way? In class? No, don't worry that. Okay, then AX is equal to AY. So A times X minus Y is equal to 0R. Now, since A is not a zero divisor, what should X minus Y be? 0. Since A is not a zero divisor, X minus Y is equal to 0R. So X is equal to Y. So F is. Okay. Yes.
When we go from AX equal to AY, so A's reference X,
Yeah.
right? We have to say because
It's not commutativity here.
No.
It's the distributivity.
yeah, it's
No. This I assume you know. Okay, this I assume you know. Okay, great. Now, to show that if R is finite and A is not a zero divisor, then A is a unit. If R is finite, of course, R is assumed to be commutative, and A is not a zero divisor, then F is, what can I say about F? What the first part? Before?
Look at
Is objective. F from R to R is injective. Now R is finite, so F is surjective. So there exists x0 in R such that f of x0 is equal to 1R. So ax0 is equal to 1R. Now, since R is commutative, this means that A is a unit. So ax0 is equal to x0 in 1R. So A is a. Okay. Yeah, Emily, I said many times the first three questions are going to be from the notes. Said that. Did I say that? Many times, yeah. Many times. So the first one will be on groups, post midterm, and the next two will be on rings. One from the first part of rings, and then from the well, I mean, technically, you have in non-commutative ring, you have a concept of right and left units. So here, it's good to say it, but I won't, like, if you don't say it, I won't realize. Okay. No, I could just ask this. If A is not a zero divisor, I could just ask a question like that before.
Oh.
And that's a part of a group, right? It's not a thing, okay?
Okay.
Okay. So far seems fair. Yeah. Okay. Okay, yeah, thank you, Victor. Yeah, for the answers. Very good. Okay. Amy, is that clear now? Okay, thanks. Okay. Great. Now let's look at the exercise one. Let n equal n, and let Sn be the symmetric group on n letters. Let n be strictly bigger than 2, and H a subgroup of Sn of index m. What is the question? Show that m is bigger or equal to n. Yeah, thanks, Theodore. Yeah, thank you for answering. Yeah. Okay. Now this one looks familiar, right? This one has been done in a homework, but in the homework you've had a harder version. You remember this? Let's do this. Here, what we need to do, the coset representation. The action of Sn on the left cosets of H on Sn mod H. And it's quick. It's very quick. Action of Sn on Sn mod H. You'll take G in Sn and a coset XH. G star XH is equal to G XH. So this is in G. This is in Sn. This is in Sn mod H. Sn mod H. But using G. X is in Sn, and G is in Sn. Induces a group homomorphism from Sn symmetric group on Sn mod H. Now, what is the index of Sn mod H? What is the size of Sn mod H? If H has index m, what is the size of Sn mod H? No, Sn mod H, not the symmetric group of Sn mod H. If H has index m, so exactly. So this is this group, this symmetric group on m letters is on Sn mod H is isomorphic to Sm, right? Yeah. The group homomorphism from Sn to Sm and mod H whose kernel homomorphism rho with per row container. Now, what do I know about Kerr row? Kerr row is a normal subgroup of Sn, right? Kerr row is a normal subgroup of Sn. Now, n is equal to 10. So, what are the possibilities of Kerr row? N is 10, really bigger than 5. Kerr row is either the identity or Kerr row is an or Kerr row is Sn. Now, why can I eliminate an and Sn? Anybody wants to help? Why? Yeah.
M is strictly greater.
M is strictly greater than 2, right? Now we know that Sn Kerr row is greater or equal, is divisible in fact, by Sn H, which is M. And M is strictly greater than 2. So can Kerr row have index 2? Can the index of Kerr row be 2? If Kerr row is an, what is the index of Kerr row? 2, right? Kerr row is an. What is the index of it? N. Sn an is equal to 2. And the index of Sn in Sn is 1. What can I say about the kernel of rho? What is the only one? What is the only normal subgroup with index strictly bigger than 2? What is it? So Kerr row is equal to the identity. So what? So rho is, what can I say about if the kernel is the identity? What can I say about rho? Injective, very good. So rho is injective. So if rho is injective, what can I say? Let me continue here. And the size of rho of S, then Sn, and the size of Sn, which is n factorial, which is equal to the size of rho of Sn, divides the size of Sm, which is n factorial. Agreed? If n factorial divides n factorial, what can I say about n and m? N is less or equal to n. If n factorial divides n factorial, what can I say about n and m? That n. Okay. Are we good? This is what I need to prove. I need to prove m is bigger or equal to n. M is bigger or equal to n. Okay. You could do that. Less or equal, not necessarily divides. Yeah, sure. Okay. Very good. Is that good? Because n is equal to 10. Well, n is for any n bigger or equal to 5, the normal subgroups of Sn are 1, an, and Sn. And this is true for n equal 3 as well. Okay. For S4, you have one more normal subgroup, which is what is the more normal subgroup of S4?
It's S4.
Yeah, we remember what's the subgroup of S4 that is normal that has size 4? We remember it? The 3 subgroup, the 3 2x2 cycles, right? Yeah. 1 2 3 4, 1 3 2 4, 1 4 2 3, and the identity. This is a normal subgroup of S4. Okay, we should keep that in mind. Okay. Why is sim Sn mod H isomorphic to Sm? So how many cosets of H do you have? No, an Sn mod H. So H has index m, so you have m cosets, right? Label your cosets 1, 2, 3 up to m in any labeling you want, and then you get that sim Sn mod H is isomorphic to Sm. Sure. I mean, you don't have to use divide. In fact, if n factorial is less or equal to n factorial. Okay, because if m is strictly smaller than n, then n factorial would appear. Okay. Yeah, is that good, Victor? Write down m factorial. M factorial would be n factorial times something else bigger than 1. Okay, great. Okay, awesome. Now we're good. Is that good? Everybody, how do you find the difficulty of this question? Yes, Victor, exactly. Yeah, exactly. How do you find the difficulty of this question? Hard. Okay. It's a question that we did in the homework. Oof. Okay. Whoa. Okay. This is a question that was done in the homework. Okay. Yeah, it's a question. Even in the homework, it was trickier, right? The homework was trickier. Okay, great. But you see, it's not very long. Now let's move on to exercise 5. Exercise 5. 1. A GBA group, show that G acts on itself by conjugation. And that a set of fixed points this action is the G. Now, how many times do we do this? Okay, you can expect like things we have done a lot of times, or it's something we did a lot of times. It's I mean, I did a lot of things a lot of times, so it's
Can you put this question?
yeah. I could put something like okay. The GBA group, so that G acts on itself by conjugation, and the fixed point is that G. So I'll do this here and then do part 2 after. Okay, so what is conjugation? You should know what conjugation is. So define the action, define function from G plus G. G is in G and X. The G star X. What is G star X by conjugation? What is it? That's the inverse, very good. Now, what do I need to show? First, I need to show that EG star X, so GX, G, X, G. So that X being G. What is EG star X? So just EG X, EG inverse is X. Now let G1, G2 be in G. What is G1 star G2 star X? This is G1 star G2 X inverse, which is G1 G2 X to inverse G1 inverse. Now G2 inverse G1 inverse is just G1 G2 inverse. It's just G1 G2. Okay. So G acts on G by conjugation. So G acts G. Okay, can I erase here after? Everybody attending online, can I erase the board? Okay. Great. Now, X in G is a fixed point. X in G is a fixed point of star. If and only if what? If and only if G star X is equal to X for all G and G. Right? Everybody? If and only if Gx G inverse is equal to X for all G and G. If and only if Gx is equal to Xg for all G and G. If and only if X belongs to the G. What does it mean to be a fixed point of star? What it means to be in the center. Hence, the set of fixed points of star that is such. Okay. Now part 2. Let's look at part 2. Let P be a prime number. K is an M. Let G be a finite P group of size of order P to the K. Show that ZG is equal P to the M for some M and N, and deduce that ZG has an element order P. Was this question okay? Yeah, this question was okay. Okay. Yeah. So let's prove it. Now, how do we prove this? Again, what's the most important theorem here? I have a P group acting on a finite set. Right? G is a P group, you agree? And G is the finite set in this case. G is a finite P group. Acting on the finite G set, which is G. By star, right? Agree or not? By the first part. G acts on G by conjugation. What is the set here? What is the set on which G is acting? G acts on G. What is the set on which G is acting? It's G, right? It's exactly, which is G by star. The set of fixed points is ZG. Hence, what is the size of S? What is S in that case? What is the G set? G set is, what is the G set in that case? G is acting on one set. G. Hence, the G set is congruent to the number of fixed points. If ZG is the set of fixed points, how many fixed points do I have? The size of ZG. Agree? If G is a P group acting on a finite G set, then the size of the G set is congruent to the number of fixed points, what P? Yeah, exactly. And then I applied it here. Now G, what is G? G, what is G mod P? G mod P is what? Look at G here. G is a finite P group. Okay, so what is G mod P? 0, yeah. So ZG okay. So ZG is divisible by P. The size of ZG is divisible by P. P divides G. Now, by Lagrange, where does ZG belong? On ZG divides the side of G, which is indicated. So ZG, I'll erase here. What are the divisor of P to the K if P is prime? So these are just one, P squared until P to the K. Agree or not? If P is prime, what are the divisor of P to the K? These are the divisor of P to the K, right? Now, if ZG is congruent to 0 mod P, what can I eliminate from here? What is the one that I can eliminate? What size I can eliminate? No, you don't have to prove it. You can just use it. Sure, yeah, parser, sure, but I prefer that you show it. Now you can do it from here immediately. You can do it from here. ZG is congruent to 0 mod P, and ZG belongs to 1 P squared P to the K. So can ZG be 1? Okay. Exactly. Very good. Since ZG is congruent to 0 mod P, then the size of ZG is different than 1. So ZG has size P to the M for some M between 1 and K. That's it. That's it. Now, why can I say that ZG has an element of order P? No, but why does ZG have an element of order P? Cauchy, right? By Cauchy, yeah, exactly. Yeah, ZG is a subgroup of P. So ZG is a group. And G is a subgroup of P. And has order divisible by P. By Cauchy's theorem, ZG has an element of order P. Oh, you mean a subgroup, so that you want to say it's finite, basically. Okay. So ZG is finite. Okay. Yeah. Okay. Very good. Very good. Very good. Very good. Yeah. See the word Cauchy a lot. Very good, everybody. Very good. Any questions on this? Yes, yes, exactly. Victor, yeah, you're right. Yeah, exactly. This is why I don't insist on it. Could we have used the class equation? Sure, you could have used the class equation. Yeah. Why? Could I explain why 0 is equal to ZG mod P? So you have a property. If G is a finite P group acting on a finite set S, then the cardinality of S is congruent to the number of fixed points modulo P. Yeah, yeah. This is just the orbit stabilizer, or this is just that the set is a disjoint union of orbits, and you separate into orbits of size 1 and orbits of size bigger than 1. Yes, Victor, but that's only for P groups. How do you show it's bigger equal to P? Because ZG is congruent to 0 mod P. It cannot be 1. Right? Jan, you can go to the lecture by lecture on their course outline. There's a detailed course syllabus. Okay, and then you can see the lecture. But should be something post-midterm. But if, for example, I use the fact that ZG is a subgroup of G, it must divide P to K, how do I show it's bigger than P? Did I answer the question? Did I answer the question? If ZG is congruent to 0 mod P, can ZG be equal to 1? No. And what are the possibilities for ZG? These are these. So if ZG is not equal to 1, it must have size P to the K. It must be a power of P. So if G is a P group, then ZG is not 1. Sure. Okay. Yeah, sure. That's okay. Yeah. Okay. That shows me that you studied. But I mean, here it's the proof is not bad. Okay. I mean, this is the proof that the P group has no trivial center. This is the proof, right? But anyways. I mean, yeah, the point of the question here is just proving that property, if you want. Okay, great. Any questions on that? How do you read the difficulty of this question? It's fair, right? This one is fair, or this one is fair? This one is fair, everybody? It's all right. One is easy and 2 is medium. Yeah, first part 1/10. And the second part, yeah, but and they have the same weight, right? So, yeah. Okay, now we use what question? Exercise 6. Yeah, this is the hard one here. Yeah, this is the hard one. Okay, great. Okay, so you can expect a question of this difficulty tomorrow. You can expect something like this question. Okay? Maybe it's the same, who knows? But you can expect a question of this level. And what is the key theorem here? What is the key theorem? If G is a finite P group and S a finite G set, then the size of S is congruent to the number of fixed points mod B. Yes. Yes. I can ask you first part, prove it, and second part applies. Okay? So please, this is an important result. Okay. Now, this is a hard one. So you won't have anything of the difficulty of 2 tomorrow. Okay? You won't have something that difficult. 2 is very difficult. It was in your original final. But 1 and 3 are okay, yeah. And if you notice that I diluted the difficulty of 2 by 2 easier questions. 3 is not 3 is fair. 3 is a very fair question. 3 is a very fair question. Okay. It's 6. FP prime and FP, the field Px. And let R, oops, I made a typo here. The X should be small. Anyways, let R equal FP of X. Polynomial ring over FP. Okay, I'll just write it this way. Write it better. So with coefficients in FP, let f of x. This is a nice one. R and I, the ideal generated by f. Okay, so for part 1, did we have a difficulty? For part one, is it difficult? Okay, of course I'll do it. Now, is in the first copy I just wrote f3 of x mod x squared minus x plus 1 is isomorphic to f2 of x mod x squared plus x. Now I modified it, I just put the same f2 because there was a typo. So let's do it here. 1. Show that f of x is irreducible in R in f of x. And the second part of 1 is the ring f2 of x modulo x squared minus f plus 1 isomorphic to the ring f2 of x mod x squared plus x. Okay, so any volunteer, just anyone, maybe from the chat, can help me with 1. How do I proceed? How do I show that? Let's say for p is equal to 2. Exactly, this is what you use. Very good. Very good. Awesome. You just check them one by one. And then how do you do the second part? This, yeah, very good. So the ring f2 of x mod x squared minus x plus 1. One is a field and one isn't. Very good. Very good. Very good. Very good. Exactly. Awesome. This is very good. Yeah. So this you should expect how to do. Now can you show immediately it has no roots? You can show it has no roots, but can you show immediately it has no roots? For any p, it doesn't have any root, by the way. For any p, this doesn't have any root. And in fact, for any p, this has the value 1. Let's prove it. Do you want me to do a particular proof for p equal 2 or p equal 3, or a general proof? Let's do a general proof, okay? Okay, let's do a general proof here. Any prime p, f of x has no roots in p of x. Let's prove this. Let a be in fp. What is f of a? F of a is a to the p minus a plus 1. What is that? What is that? A to the p minus a, what can you say about this? This is always 0. You see that? Factor an a out, you get it's a to the p minus 1 plus 1. If a is 0, then this whole thing is 0. If a is non-zero, by Fermat's theorem, this is 0. By Fermat's theorem, this is equal to 0, right? A to the p minus 1 is equal to 1. And if a is 0, this is 0. So this thing is always 0. A to the p minus a is always 0. If a is 0, then a to the p minus a is 0. And if a is different than 0, a to the p minus 1 is equal to 0. Exactly. Are we good here? People attending online virtually, are we good? This is a general proof. Now, if you cannot find a general proof, you can just plug in the numbers. Okay? You can just plug in the numbers for p equal to 2 or 3. Now, if p is equal to 2 or 3, and f of x has degree p and no roots in at p, then f of x is irreducible in f of x. Okay? Now, the second part is the ring f(2) of x mod x squared minus x plus 1 isomorphic to x squared plus x, f(2) of x mod. Anyone here wants to help? No, we're doing it, but anyone here wants to help? Yeah, I did this, no? Did I do it, though? If p is 2 or 3, and f of x has degree p, and it has no roots, so it's irreducible. So anyone wants to help for the second part? Anybody wants to help? Yeah, no,
No, go ahead.
Well, I mean, the first one, do you need to plug in the numbers or you find it already from before? Yeah. The first one, is it a field? Is the first one a field? Exactly. And is the second one a field? Exactly. Very good. Hence, f(2) of x mod x squared minus x plus 1. This is just for p is equal to 2, right? This is for p equal to 2. Is a field. But f(2) of x mod x squared plus x is not a field. Since 0 squared plus 0 is equal to 0, right? It has a root, right? It's a degree 2 polynomial with a root, so it's irreducible. It's reducible. What you can do, you can also factor it. So they're not isomorphic. So are not isomorphic rings. Okay. So far, so good? Yeah? Okay. Great. Now the heavy question. Now the heavy question. It's a bit heavy. And it's a bit unfair. But pardon me? No, it's a lot. It's a lot. Yeah, it's a bit hard. It's a bit hard. It's a bit hard. So okay, are we ready? What if it were on f(3) of x? f(3) of x, well, you have what do you mean? f(3) of x mod x cubed minus x plus 1? Okay, great. Let's look for 2. Yeah, x cubed minus x plus 1 would have no roots in f(3), not x squared minus x plus 1. The p should match the p. So f(3), x cubed minus x plus 1. Okay. Are we good here? Guys, are we good? So anybody attempted 6.2? Yes, exactly. Should match the p. Anybody attempted 6.2? No. Okay, so what we have to do is kind of a group action, and we have to carefully choose it. Okay? We have to carefully choose our group action. Now, before, I just need a small lemma that maybe I didn't mention in class, but it's a very silly one. It's a very silly one. So if P is prime. Oh no, so show no, there. I mean, it's obvious. It's not very hard. Show that xp minus x plus 1 is irreducible in activities. Okay, this is hard. I call it f of x, right? First of all, what is f of x plus 1? I mean, you can still do it, but what is f of x plus 1? If x is in Z1, P Z as a polynomial. I mean, it doesn't. Right? Now, what do you know about this expansion? You know how to expand this one. This is just a sum from k equals 0 to b. B choose k, x to the k, minus x plus 1, plus 1. For k equals 0, this is b choose 0, x to the 0, which is 1, plus b choose b, which is also 1, x to the p, plus the sum as k equals 0, b, e to the k, xk, minus x plus 1, plus 1. So b choose 0 times 1 is 1, right? You know what the polynomial coefficient is, right? B choose 0, this is 1. So this one will cancel out. And what do you get? You get xp minus x plus 1 by just regrouping these, plus this one. Oh, sorry, plus sigma k equal 1, this one. Great. We know what the binomial coefficient is, right? Oh, wait. This is p choose k. This is just p factorial, k factorial, plus p minus k factorial. Okay, great. Now notice that if k is between 1 and p minus 1, then p choose k factorial, p minus k factorial is equal to p factorial, right? Just rearranging these. Agreed? Just rearrange them, multiply this, the cross product. P factorial is this times this times this. Then, since p divides p factorial, then p divides p k, e choose k, k factorial, and p minus k factorial. Now, if a prime number divides a product of numbers, what can I say? It divides at least one of them. Hence p is prime. P divides at least one of these two, right? One of these three. You agree or not? P is a prime number dividing a product. So P must divide at least one. Now, if K is less than P and bigger than 1, can P divide K factorial? No. Can P divide P minus K factorial if K is bigger than 1? No. So what must P divide? P choose K. And P is prime. And P doesn't divide K factorial. And doesn't divide P minus K factorial. What can I say about P divides P choose K? Hence, what can I say about this part? If all of these are 0 in FP. These P choose K, are they 0 or not? Everybody, what can I say about the right hand side? If P divides P choose K. If P choose K is divisible by P, what can I say about this expression at the end? What can I say? This one is 0 here, right? This one is 0. What can I say about this entire thing? It's 0. So what can I say about f of x plus 1? Is equal to, can I erase here? Everybody, can I erase here? Or I'll write here. Hence, f of x plus 1 is equal to xp minus x plus 1 plus sum k equal 1 p minus 1 into scale xk. Now this is 0 in FP, right? Agree? This is 0 mod p. We proved this here. Right? So this is just xp minus x plus 1. Just f of x. Okay, this is just an example. Now, similarly, I'll erase here. I did this example just to motivate this choose coefficient. Okay, just to motivate this choose coefficient. Now, for any j in x in FP, f of x plus j is equal to x plus j p minus x plus j plus 1. Now, if you look at these binomial coefficients, if you do the same binomial expansion, what can you say about x plus j to the p? This is x to the p plus j to the p plus some stuff here. X to the k, j to the p minus k, yeah, to the p minus k, minus x plus j plus 1. This stuff is 0 by the previous lemma. So this is just x to the p plus j to the p minus x plus j plus 1. Great. Now j to the p, what is it equal to? It's equal to j, right? Because j is in fp. So this is xp plus j to the p minus x, oops, this is j, minus g plus 1. So this is f of x. So if you translate f of x by any j in fp, you get back f of x. f of x is a constant function, not constant, is as a function, yes, but not as a polynomial. Okay, as a function, yes, but not as a polynomial. Polynomial, it has degree p. A constant function has degree, well, you know, a constant function is a function. Okay, very good. Now, J is in FP, right? What is J to the P? No, if J to the P is equal, if J is invertible, then J to the P minus 1 is 1. Multiply J by both sides, you get J to the P is equal to J. And if J is 0, then J to the P is equal to J. Okay, both are equal to 0. Great. Now group actions. Now group actions. A J of x be an irreducible factor of f of x. Now here it's very clear that you can irreducibility is not affected by shifting, right? If you shift everything by 1, you still can't factor it. Agree with that? Then J of x plus J is an irreducible factor of f of x plus J is equal to f of x for any J in FP. Agreed? Agree? Everybody, do we agree? Everybody? Okay. Now, hence, Z must be Z here, I'll just because I'm right as a group, acts on the set of irreducible factors on the set of irreducible factors of f of x. Basically, if g of x is an irreducible factor of f of x, then g of x plus j is an irreducible factor of f of x. And that's an action, right? You can check that it's an action. If g is an irreducible factor, and you define g star g of x to be just g of x plus j. And it's clearly an action, right? You're just translating. Here the ZP is addition. This is clearly an action. Okay. Now, what can I say about the orbits of this action? What are the possible sizes? Z mod PZ is acting on the set of irreducible factors. What can I say about the orbits of this action? They are 1, 4, peak. Am I the only one who likes this? Maybe? I don't know. Yeah. Now, the claim is that g of x cannot have orbit p. Why there is no orbit of size p? No, it wasn't the final, but I gave you the steps. I gave you the steps. I gave you all the steps. I gave you step by step. I gave you step by step. It wasn't the original final, but I gave you step by step. Don't worry. Tomorrow is gonna be easier than that. Trust me. Okay, so Clearly an action. G of x irreducible. This is clearly an action. Now, suppose this action has an orbit, hence any orbit size 1 or p. Now, how many irreducible factors in fp of x? How many irreducible factor does f of x has at most? It has at most p irreducible factors, right? Because f of x has at most p roots in a field. The set S. Now, S is size at most p. Suppose this action has an orbit of size p. Then f of x has p distinct irreducible factors. Now, since f of x has degree p, what can you say? If it has p distinct irreducible factors, it means it has at least a root, right? All the factors would be linear, right? If you have a degree p with p distinct irreducible factors, all the factors would be linear. Okay. F of x have p distinct linear factors in fp of x, implying that f of x has a root in fp. Can f of x has a root in fp? Can f of x have a root in fp? No, because we proved contradiction. So all the orbits, if they don't have size p, any orbit, what is the size? Any orbit has size 1 or p. Now you cannot have an orbit of size p. What is the size of an orbit then? 1. And then we will show that you have only one orbit of size 1. Now g of x is an irreducible factor. So if g of x is an irreducible factor, of f of x g of x, then orbit of g of x is just g of x, right? Because any orbit has size 1. This means that next g of x plus j is equal to g of x for all j in fp or in z1 pz, right? I'm using here for the groups. Great. What can I say here? Then, what can you say here? Then j of 0 is equal to j of 1 is equal to j of p minus 1. Because if you plug in x is equal to 0, then you get g of j is equal to g of 0. Therefore, what? Therefore, g of x minus g0 has p distinct roots in fp. Right? Now, what's the smallest polynomial that has p distinct roots in fp? Yes, we're on the same question. Yeah, it's a. Well, it's xp minus x, right? So gx minus g0 belongs to the ideal generated by xp minus x. Since xp minus x is equal to x times x minus 1 times x minus p plus 1. Now g of x has degree at most p. Degree of g is at most p because f has degree at most p. So g of x minus guys minus g0 is xp minus x if g of x is 1. If it's not 1, that's not a, and just make it 1. And hence g of x minus g0 is xp minus x plus g0. This was a hard one. Yeah, you won't have something like that. But I mean, this is just 5 points on 70. Hence, g of x is xp minus x plus g0. Now, g of x has the same degree as f of x. Is degree f of x. And g of x divides f of x. So f of x is equal to g of x, and both are harmonic. Okay? So f of x is equal to g of x. What did we assume first? We assumed that g of x is an irreducible factor of f of x. So if g of x is an irreducible factor of f of x and f of x is equal to g of x, then f of x is irreducible. I mean, if this is tomorrow, you know how to do it, right? This is tough. Okay. No, I'm kidding. You're not gonna. This is not gonna be tomorrow. This is not a question tomorrow. 6.2 is not a question tomorrow. Okay. I mean, I just wanted to make a point that there is a question that will make you think, and you will have a question that will make you think. Okay. So it's on 5 points, in my opinion. Yeah. No, I said this is harder. The practice. I wouldn't say much. I wouldn't say much. No, I wouldn't say much. Okay. Yeah, I mean, no, even, yeah. So even this 5 points, there were in the original final, and there were no objections to them. So like, okay, great. Now we're done with this. But I agree. So 5 points, you can expect 5 points to be a bit tough, or to be a bit like you should think of them. Maybe not very tough, but you should think of it. And it's 5 points on 70, so it's very fair, in my opinion, right? You have 10% that is not that you have to think about, right? It's not. But here, everything has been seen in the homework, right? Like question 1 to 5 have been seen in the homework and in the notes. 6 is a bit original, but 6b, only 6b, that is that you haven't seen. Okay. Now let's look at 3. Let k is equal to r mod I is fp of x mod f of x, where p prime from 1 to 3. This is fair game. This is fair. Is this? Do we know? Did we get this or not? The question part C.
I really got it yesterday.
Because we did yesterday. Oh. So where P is a prime congruent to 3 by 4. Does there exists A in K or A in R mod I such that a squared is equal to minus 1 plus 9. Yeah, 6.2, I think. It's not that I caught, I mean, you know, it's, I mean, it follows from more general theory, but, yeah, the question I came up with it myself. It's not like the proof I came up with it myself, but I think it's a known proof. It's not that I came up with it, but I tried to use group actions on it, and it's a particular case of something that is more general. So, okay. Great. Does such an element exist? Can I find an element such that a squared is minus 1 plus I in this ring? I don't remember. I mean, again, you should not worry about the hard one. Worry about the easy ones first. Worry about the 55 that you have seen, and then worry about this is how we should go about that. Exactly, Victor. Exactly. Since you have no element of order 4 in this ring. Very good. And multiplicative. Okay. Now f of x is irreducible in p of x. So fp of x mod f of x is a field with how many elements? How many elements does this field have? Anybody can help? Maybe online? I'll take anyone here. How many? E to the p, right? Is a field with e to the p elements. Okay, this is R mod I, right? R mod I. Now, what can I say about the group of units of this thing? How many elements does it have? How many elements does the group of units of this thing have? No, it's a field. So how many? P? P to the p minus 1. Is that right? You see that? The group of units of a field, of a finite field, is everything but 0. So how many elements do I have here? P to the p minus 1. Hence, the group of units R mod I is just R mod I minus 0 plus I, and has p to the p minus 1 elements. Okay. Now suppose there exists A in R mod I such that A squared is equal to minus 1 plus I. Of R mod I, I'll just little this about R mod I star if I did. A squared is equal to minus 1 plus I. Can A be 0? If A squared is minus 1, can A be equal to 0? Then A is different than 0 plus I. Since 0 squared is I, it's 0 plus I. Now, can A be equal to 1? If A squared is minus 1, can A be equal to 1? No. And A is different than 1 plus I, since A squared is minus 1 plus I is different than 1 plus I. Why is minus 1 different than 1? Because 2 is different than 0, right? You agree? Since 2 is different than 0. Because E is 3 and 4. E is an odd prime. Great. Now, what can I say about A to the 4? A to the 4 is minus 1 plus I squared, which is just 1 plus I. Hence, A belongs to R mod I star. And has order dividing 4. Now, does A have order 1? Does A have order 1? Is A equal to the identity? Now, is A squared, does A have order 2? A doesn't have order 1. Since A is different than 1 plus I. A does not have order 2, since A squared is minus 1 plus I, different than 1 plus I. So what can you say about the order of A in R mod I star? It has order dividing 4. It's not 1. It's not 2. What is it? 4. Then A has order. The group in the multiplicative group, R mod I star. So what can I say about 4 in R mod I star? 4 must divide. And 4 divides the cardinality of R mod I star, which is P to the P minus 1. Now, P is congruent to 3 mod 4, which is congruent to minus 1 mod 4. Wait a minute. Yeah, okay. P to the P, what is it congruent to? P to the P is congruent. Now, what can I say about P to the P? What can I say if P is congruent to 3 mod 4? P, what can I say? Is it even or odd? It's odd, right? If P is 3 mod 4, then P is odd. So this is congruent to minus 1. P is odd. Hence, P to the P minus 1 is congruent to minus 2 mod 4 is congruent to 2 mod 4. So does 4 divide P to the P minus 1? I get here that 4 divides P to the P minus 1. But here, does 4 divide P to the P minus 1? No. So you have an element satisfying A squared is equal to minus 1 plus I. Okay. Are we good? Where's the point? Is it the congruence point? Is it here? Until here we're good? Where? Where exactly? The proof is written here. Okay, so that's a fair question for tomorrow. Tomorrow you can expect a question like that. Okay. Yeah, but here I'm justifying way more. Here I'm justifying way more. I'm justifying way more. So you have that 4 divides R mod I star P to the P minus 1. and then p to the p minus 1 is not divisible by 4. So you get a contradiction. I mean, you know, on the final, for example, you can say if a is equal to minus 1 plus I, if a squared is equal to minus 1 plus I, then a has order dividing 4 since a to the 4 is 1 plus I. And you can just immediately say, since a is different than 1, and a is different than and a squared is different than 1, a doesn't have order 1 or 2. So a must have order 4. Pardon me? Here? What do you mean? Like what to write on the final? No, I mean, yeah, I mean, here you just have to show that a has order 4. Right? Show that a has order 4, and then r mod I star doesn't have orders divisible by 4, and that's it. You can say r mod I star has order p to the p minus 1, right? Which is not divisible by 4. Hence has no element of order 4. Now, if a squared is equal to minus 1 in r mod I star, then a must have order 4. Since a is different than 1 and a squared is different than 1, but a to the 4 is 1. Okay? This is what you could write. But I mean, if I want to justify it here, it will take longer because I just don't want to say it verbally. Okay? But I mean, this is for this question. If I change the question, then it's okay, but this is fair game for tomorrow. This is fair game for tomorrow. Pardon me?
Visual question?
No, normal question, yeah. I mean, we've done this many times. In the ring practice sheet, we've done this many times, right? In the ring practice, this question, this order 4 business has been done many times. Right? Yeah.
And it's recorded too. So
yeah. So it has been done many times. And we did something with order 3 as well. So you could expect something like that. So if you have something like that, then you should. I might give you a hint. If I give something like that, I might give you a hint. For example, consider the order of such an element. Okay, now let's do the last question. How was the last question? So first of all, how do you rate the difficulty of this final? From hard to too hard to medium to fair to easy. It's not easy. We'll eliminate easy. But medium or hard or too hard? Hard. Hard but doable.
hard but possible.
Hard but passable.
Yeah.
Hard. Okay, so do you find getting a passing grade, getting 35 on 70 very easy? Yeah, exactly. So I told you, sit down for, did you guys sit down for 3 hours and tried it? Yeah, but okay. Yeah, but no, don't say that. Don't say that. Don't say that. Don't say that. Okay, this is a more or less. Okay, is exercise 7 clear or not? But so question 3 of exercise 7, is it clear or not? Construct a surjective group homomorphism from S4 to S3. Isn't that a question we did like many times? That's here you can do the question many times. So question 4. Show that there are, well, let's go. Okay, 7. Show that there are 3 elements in the conjugacy class of sigma is equal to 1, 2, 3, 4 in S4. What is the size of the centralizer of sigma? What's the size? So what are the elements in the conjugated class of sigma in S4? These are the only 2 by 2 cycles, right? How many 2 by 2 cycles do I have? 3. The elements in the conjugated class are?
And that's enough for the optics. Or
Yeah,
you
that's
just
enough.
say it's the
That's enough.
same
You just
structure,
write it down.
same structure.
That's right. I understand. 1, 2, 3, 4. 1, 4, 2, 3. 1, 3, 2, 4. What is the size of the centralizer of sigma? 8, right? The size of the centralizer of sigma has size S4 divided by the conjugation is an action. So this is an orbit, right? Divided by the conjugacy class, the size of the conjugacy class of sigma, which is 24 over 3, is 8. Is that a fair question? Is that a fair question or not? Yeah, that's because there was a hint. Okay, yeah, I mean, I can give you, yeah, it's possible that I give you a hint. Yeah, yeah, I will give you hints sometimes. So you should trust that you should expect no big surprises tomorrow. And I'm honest about this. This is harder than tomorrow. Okay, for every element in the conjugate class of sigma, write down its centralizer explicitly. You don't need to justify your answer. Now, how many groups of order 8 do I have in S4? 3, right? Everybody? Not very easy, but doable. Yeah, it is. It is. I think it is doable. I think you can get maybe 45 to 50 on 70 if you studied a bit easily. Easily, I'm saying. If you studied the things, 45 to 50 on 70 should be easy, no? Easy. I mean, I'm not saying hard. Anyways, but that's my opinion. Tomorrow it will be easier than that. Okay? Trust me that tomorrow is easier than this. Okay? It's not question by question, but overall it's easier and shorter. It's way shorter. Way shorter. Okay, so for every element in sigma, write down the centralizer and the constant. Write down centralizer is D. Okay, so first, how do we write down the subgroups of order 8 in S4? How many subgroups of order 8 I have in S4, everybody? Just let's take the people from the chat. How many subgroups of order 8 in S4 do I have? How many? Everybody in the chat? 3, very good. 3, yes. Okay, now how do I write them? What are they all? They're all what? What type of group they are? U4 thing, exactly. And how do I find 3 distinct groups? What do I do by this with the square? Exactly. No. Oh yeah, exactly. So I relabel it. That's what you, yeah, exactly. I relabel the square. So first of all, I have 1, 2, 3, 4. I want to call it H1, let's say. So anybody can help me? I have the identity here. 1, 2, 3, 4. 1. Then let's R squared doors. Could do this is R. What is the square of it? Or 3 to 1 is good, but I'll just add it. Okay, this is what I meant. You have r squared, r cubed, and then what do you have? Very good. Then?
Like
Yeah, very good. And then?
2, 4.
Very good. H2. Anyone wants to help? How do you want to label your square? Who wants to help? Who wants to help?
We can do 1, 3, 2,
1, 3, 2, 4. You gotta do 1, 3, 2, 4. Very good. Okay. You have 3 subgroups, by the way, by Sylow's theorem, right? Sylow's theorem tells you that you have 1 or 3 subgroups. Now, are any of these normal? Is any of these subgroups normal? None of them is normal. That's right. Okay, so H2, you want to help? Yeah. Anybody wants to help? I have the identity. 1, 3, 2, 4. 1, 2. Very good. Then what as well? 1, 4. 1, 4. 3. Then what do you have? Let's follow this. So we have vertical, you do vertical. What do you get? 1, 3. Oh, this is horizontal, sorry. 1, 1, 4, 2, 3, right? Okay, let's do the vert. 1, 3, 4. Then 2, 4, which is diagonal. So you get 2, 4 is this area. 3, 4. And 1. Okay. Now H3. What is the labeling that I need? Okay. What is identity? Very good. 1, 1, 2, 4, 3. Then 4, 2, 3. Very good. 1, 3, 4, 2. Let's respect what we did here. So we have, this is the horizontal. 4, 1, 3. 3, 4. Then 1, 2, and 3, 4. Very good. And 3, 4. So this is 2, 3. Oh yeah. 2, 3. Very good. Now, which one centralizes each? So sigma must commute with one of these, right? Each one centralizes sigma. How do I find it?
R squared.
You can look at r squared, right? You know that r squared in a dihedral group commutes with everything. So if you manage to write this sigma as your r squared, right? If you manage to write this sigma as your rotation squared, then this would be the stabilizer of sigma. So 1, 2, 3, 4. What is the centralizer of this one? To what does it correspond to the rotation squared? And what of these groups? H2 centralizes. This one centralizes which permutation? 1, 3, 2, 4. And then this one centralizes which one? Okay, done. Yeah. Why? It's the centralizer. This is the centralizer of this one. What is the centralizer? It's a set of elements that commutes with this one in S4. Any element in H1 is the set of all elements in S4 that commute with this one. Okay?
So like any other H1 times
Yeah.
the centralizer will equal to
Anytime any element of H1 times this thing, right, is equal to this thing plus the same element. Okay? Is this fair or not? Yeah. AB is equal to BA for all A in the centralizer of B. Okay? This is a fair question. Everybody, isn't this a fair? Oh, so you know that the rotation squared, basically. I mean, that's one way. You know that the rotation squared in a dihedral group commutes with everything, right? Because it's a singleton conjugacy class. You have seen this many times, no? In dihedral group D4, the rotation squared is a singleton conjugacy class. So it commutes with everything. Now you know that the centralizer has order 8. So it must be one of these. Now, if you manage to express this as the rotation squared in your dihedral group, you win. Okay? Great. Now use the previous part to construct a surjective homomorphism from S4 to S3. Now here you can do it in many times, in many ways. I will do it in 2 separate ways. Everybody, is the part C correct? Is part C okay? Victor, the label doesn't, the clockwise or counterclockwise doesn't matter. Okay? If you have 1, 3, 2, 4 clockwise, 1, 3, 1, 3, 2, 4 clock. Oh, 1, 3, 2, 4 clockwise, and you have 1, 3, 2, 4 counterclockwise, is the same symmetry group. Right? You see this? Yeah, but that's a very good question. We should always pay it. So what really determines is your corners, is the two vertices. Choose 2 opposite vertices, and the other will be chosen for you. Okay, that's a fair question, no? Yeah. So centralizer means that you know that the centralizer of this one has size 8, right? Now you know in the dihedral group, the rotation squared is a conjugacy class on its own. You remember this? So when you wrote down the conjugacy class of dihedral groups, you remember you had 2 singleton conjugacy class, E and R squared, right? Now, if you manage to express this E into an R squared of your square, then you win. Because a singleton conjugacy class will commute with everything. Or, let's do another way. You agree that 1, 2, 3, 4, that all of these 3 commute with each other. All of these 3 commute with each other. Great. Now, and all of these 3 are present in all the groups. Is that all right? Great. Now, so if 1, 2, 3, 4 commutes with the rotation, then it commutes with the whole group because it's commutes with one reflection and commutes with the rotation. Okay? Now, 1, 2, 3, 4, with what rotation does it commute? It just commutes with 1, 3, 2, 4. It's the square of this rotation. What's the square of 1, 3, 2, 4? Exactly. Does it commute? Does an element commute with this square? Yeah, that's it. What's the square? What's the element that centralizes 1, 3, 2, 4? So you want them to be opposite. You want 1 and 3 to be opposite. 1, 3, 2, 4. So it must commute with this rotation. 1, 2, 3. That's this one. Okay? Is it clear? Let's let more clear. Yeah. Okay, are we good here? Okay. And then you don't need to justify. You can do it the way you want. So but this is a verbal justification. Okay? But again, tomorrow it's gonna be easier. Okay, tomorrow I think it's gonna be easy. But if I tell you write down a subgroup of order 8 in S4, you know how to write it down. I tell you write down all the subgroups of order 8 in S4, you know how to write them down. Yeah. Yeah, okay. Great. 4. Use the previous part to construct the surjective group homomorphism from S4 to S3 and write down its kernel explicitly. So what do you want to use? Do you want to use the action of part 1 or you want to use part B? We have to use both, but which one do you want to use? We can do it in 2 different ways. This one is, I think, That's rejected. Okay. People attending online, is it fair or not? Yes, exactly, Victor. Yes. People attending virtually, is question 4 clear? Question 3 clear? Part 3, is it clear?
It should be.
It should be. How many times did you do part 3? Part 3 is S4 to S3.
I've seen it.
Yeah, part 3 we did like 4 times. Okay. So what do you mean the numbers? In the H's? In the H's? Oh, in the H's. So what are the symmetries of the square? You have the vertical one, and you have the horizontal one. You have the diagonal one, D, and you have D prime, and you have the rotation squared, rotation cube, and so on. This is how we get them. Come in. Okay, maybe they need to. Great. So let's do the last question. Should you do the last question? Okay. I'll do it different. I'll do it using part B only. Okay, I'll do it using part B. Okay, I can do it using part A as well, but I'll do it using part B. Okay. S4 acts. This is way 1. On S4 modulo H by G H1 here. G X H1, G and X and S4. Oh man, okay. Erase them, which induces a homomorphism rho from S4, the symmetric group of S4 mod H, which is isomorphic to what? The symmetric group of S4 mod H is isomorphic to what? S4 mod H, S4 mod H1, how many elements does it have? 3. So a symmetric group of S4 mod H is isomorphic to S3. Very good. Whose kernel? Where? With her row contained in H1. Now, is H1 normal? Yeah, we can do, yeah, we'll do them both ways. Yeah, okay, very good. Is H1 normal in S4 or not? Is H1 normal in S4? Is H1 normal in S4? That question we did, yeah, we did many times, right? H1 is not normal in S4. Now, what is H1? 1, 2, 3, 4, right? 1, 2, 3, 4. So since 1, 2, let's say, times 1, 3 times 1, 2 inverse, which is equal to 1, 2 times 1, 3 times 1, 2. What is that equal to? So if we cycle, 2 goes to 1, 1 goes to 3, 3, 6. Doesn't belong to H1. This belongs to H1. This doesn't belong to H1. So the kernel of rho is different. As the size of kernel of rho, a size strictly smaller than H1. Now, so I mean the index of the kernel of rho is bigger than the index of H1, which is 3. And by the first isomorphism theorem, S4 mod per rho divides the size of S3, which is 6. So the index of per rho is bigger than 3 and divides 6. What is that? What must it be? If it's strictly bigger than 3 and divides 6, what must it be? 6. So a size 6. What can I say about rho? So what can I say about rho? Then rho is, or so, since it has size 6, then S4 mod rho is isomorphic to S3, right? Everybody? And what can I say about the size of rho? And rho has size S4 over S3, 24 over 6, which is 4. Now, what is the only normal subgroups of V of size 4? If I tell you use the homework, then yeah. Exactly. Then rho is normal in S4 and rho as size 4. So what is rho? Just 1. 1, 2, 3, 4. 1, 4, 2, 3. And 1, 3. Okay. Any question on that? Is that clear? Everybody, is that clear? Which one? Which one? This one? Where? Where exactly? This is important, okay? So I'd stop myself if there's something shady on this. Where? What do you mean the kernel is contained in H1? After? H1 is not normal. Yeah. You agree? So can the kernel be equal to H1? Because the kernel is normal and H1 is not. So if it's not equal and is contained, then the size of the kernel is strictly smaller than the size of H. Agree or not? A is a subset of B, right? A is finite. And B is different than A. Can B have the same size as A? Yes, size? Strictly yes. Is that clear? Now, what can you say about the index? Then the index of rho is bigger than the index of H1. Right? The index is S4 over the order of the group. So the index of rho is strictly bigger than 3. By Lagrange, by the first isomorphism theorem, S4 mod rho divides the size of S3, which is 6. Yeah. Yeah. And more than 5. So for S4, you have one normal subgroup of order 4. Okay, and that's the only one. Okay, since is it clear here? Here, H1. What is the order of H1? 8. S4 mod H, S size. 3. Is how many left quotient does H have? 3, right? 45 by 8. Clear here so far? Here is good. In this question, I did many times, so it's good to know. Okay. And you can get different. I can give you this question, the same part of that. I can give you something a bit different, or I might not give it at all. But you know, it's a good idea to know these. Okay. So, per row, what is the size of per row? Since is the only normal subgroup of S4 size. Okay, great. Oh, why can we say that Curro is contained within H1? Curro is the intersection of the conjugates of H1. Is that good? Curro is the intersection of the conjugates of H1. Everybody? Yeah, I'll do the other way now. Curro is the intersection of the conjugates of H1. So Curro is contained in H1. Okay? Are we good here? Yeah, Curro is the intersection of the conjugates of H1, so Curro is contained in H1. Are we good for the person who asked the question? Okay. Okay, thank you. Thanks, Peter. Well, exactly. Okay, so let's do that. Let's do the other way. Let's do the other way. The other way is simpler.
We still have to show it symmetric.
Pardon?
We can show symmetric.
Oh, so S4. Oh, so I did. So S4 mod per row is isomorphic to S3. So row is surjective, right? Right. Sorry. Thank you. Right. If S4 mod per row is isomorphic to S3, what can you say about row? What is exactly row from S4 to S3? And if S4 mod per row, which is isomorphic to row of S4, is equal to S3. What can you say about row? It's surjective, right? Okay, thank you. Okay, let's do the other way. The other way is nice. It's using both parts and it's quicker. Now, S4 acts on S, which is 1, 2, 3, 4, 1, 4, 2, 3, 1, 3, 2, 4 by conjugation. The conjugacy class. We agree or not? Everybody, we agree with this? It's a conjugacy class, so S4 acts on this by conjugation. This induces a homomorphism. This action induces a homomorphism. I can say phi from S4 to S, the cardinality of S, which is S3, right? Agree or not? Agree? A homomorphism from S4 to the symmetric group on S, which is S3. Agree? Everybody? What is the kernel of rho? The kernel of rho is the intersection, as S is in S, of the stabilizer of S. So these are just H1, intersection H2, intersection H3, because the stabilizer in this case are the centralizers. S4 is, yeah, it's an S4 set, so it can act on a set by conjugation. It doesn't have to be a group. It doesn't have to be a group, right? Cardinality of S. S, the cardinality of S. Here, cardinality of S. Symmetric group on S. Okay. Homomorphism from S4 acting on this set. You get a homomorphism from S4 to the symmetric group of this set. Right? Not necessarily coset representation. Now, what is the kernel of this homomorphism by the lecture notes? It's the intersection of the stabilizers. What are the stabilizers in this case? These are the centralizers that we have found in part 2. This is just H1, intersection H2, intersection H3. Now, look at the intersection. What do you get? You just get this. Okay, if you compute the intersection. Now, why is rho surjective? S4 mod kerrho has size 4. S4 mod kerrho is equal 24 over 4, which is 6, and is isomorphic to a subgroup of S3. So S4 mod kerrho is isomorphic to S3, so rho is surject. We didn't see it before, did we? I mean, we know, we have seen before that an orbit is a transitive G set, right? You agree? An orbit is a transitive G set. The orbit itself is a G set. So the conjugacy class is a G set. But here I leave you the options to do the way you want. Okay? I leave you the options to do the way you'd like. So I don't tell you use this action or use this action. It's in the homework. It's in a homework. Homework 8, part 3. It's the same as the question 2, is the same as the question 4 of this assignment, of this exam, of this practice. We say that we use the fact that the orbit is a transitive G set. For the previous way, how did we show it was surjective again? So the previous way, we showed that S4 mod kerrho is bigger than 3, and S4 mod kerrho has size and divides 6. So it must be 6. And it's isomorphic to a subgroup of S3. Are we good here? If you look at the so we did see that. So an orbit is a transitive G set, right? And someone asked me the question about this yesterday. So this is why I kind of put the question. So a person asked me this question about this thing yesterday. So this is why I put this question. Okay, great. So tomorrow expect something a bit easier. Let's say easier and fairly shorter. Okay, so it's shorter. S4 has? Because this is a conjugacy class, right? So when you conjugate these elements, you get back to these elements, right? Yeah, no, tomorrow is shorter and easier. I mean, it's shorter and easier. Some parts may slightly be tougher, but in general, it's easier. I'm confident with that. That's why I'm more confident. I'm confident that it's easier. And then will there be Euclidean theorem? No, I'm not gonna give you any question on Euclidean algorithm. I don't think so. Maybe in a proof, maybe, but not the proof of the Euclidean algorithm. No, I'm not gonna give you that. No. Yeah, but I'm not gonna give you that. Yeah, I'm not gonna give you that. Like there are 3 proofs and 4 other exercises, right? 2 proofs will be on rings, and 1 other exercise will be a ring calculations, like the thing we did today. And then yeah. And then 3 proofs, I'd say, you know, on group 2 so 3 other exercise on groups. Okay. So some calculations, some could be like these things, nice calculations, so that the subgroup is not normal, and some could be like small proofs, like exercise 4 and exercise 5 of today. Okay. Is that good? Great. People have questions. Let's see. Can you do the proof that if R has characteristic 0, if and only if 1 does not have finite order in R plus? I did this yesterday. If you can check, I did this yesterday, no? I did that yesterday. If you can view the recording, I did that at the end, right? It's at the end that I did it. I did this at the end.
It's not in.
Okay, so I did it yesterday in the notes. So what is 4? 4 is the action. What is 4? 4 is the no problem. Bye bye. 4 is the action of Sn on H, right? Is that it? 4 is the action of Sn on, if you have a subgroup H of index M, then M is bigger or equal to N. 4 fit it here. 4 is the only question that fit on this board. Yeah, it's the only question that fitted on this board. Okay. People have questions? I'll just take the questions from people attending online. How important would you say ideals are? I mean, you just should know. I mean, the principal ideals generated by f of x in ring calculations, okay? And in proofs, right? You have big theorems. If R is a commutative ring, then the only two R is a field if and only if the only 2 ideals are 0 and R, exactly. But so everybody, were the first 3 questions okay? The first 3 questions were okay.
Yeah, but if you know.
Yeah, it's a lottery, right? It's a how do you say, it's a gamble. Yeah, exactly. But I mean, if you study everything, then no, I'm personally not very worried. I hope so, at least. Any more questions from the people attending online? I couldn't find it, proof for it, and it wasn't in my notes from lecture. Yeah, no, it's not in the notes, but I did it in the recording yesterday. If you could look at the recording, I mean, you know, it's very quick. So R has infinite order. R has characteristic 0. So I will let phi be the unique homomorphism. If kernel of phi is 0. If and only if phi is injected. If and only if M, sorry, yeah, M times 1 of 0 is different than 0 R, if and only if for all of them. and Z and not 0, I can only have one arc doesn't have finite order. Okay? On the exercise 6 of the practice final, well, the ring reflects well. So I would say that 6.1 and 6.2 reflect well the problems on 6.1 and 6.3, sorry, not 6.2. 6.1 and 6.3. And the ring practice sheets reflect well the things that you can see tomorrow. Okay? Yeah, no, not 6.2. It was a mistake. I said 6.2, a mistake. Okay, folks. You guys have questions? I mean, there are only few people left here in the room, so I'll just like take the people online and then. Okay. Good night. Sleep well. No problem. No problem. All. Thank you very much. You as well. We aren't sleeping tonight. I'm living in the library. Yeah. No problem. Okay. By the way, did you guys fill in the course evaluations? Please fill them in. Where is the field house? I don't know. The field, is it the gym or the field house? Field house is the same place, but is it the gym or the field house? Field house. So do you know where intramurals happen? Okay. Okay, I see. Okay. So if you ever played like indoor soccer, mini football, mini soccer, in the gym, intramurals, it's there. And it's where you have the running thing, right? It's where you have the running track. Just follow, yeah, but there might be many crowds, right? There might be people going at other places than the field house. The gym, it's mostly the field house. And the gym, what about the gym? What about the basketball court? Isn't there many people there? Oh, okay. Okay, I see. Okay, so there'll be people guiding. Okay. Okay. Also, the course evaluations were due yesterday night. Oh, I think someone told me they're due tonight, not yesterday. Yeah, it's due tonight, not yesterday. Okay, so people attending online, do you guys have questions? I'll just have to take the questions after from people here before I close this. Okay, please ask your questions. I'll give you one more minute. If someone has a question, please send it. Tomorrow I'll be there. I'll try to be there at 9:30, 9:40. Last second hint. Oh, like a tip? I mean, study the things I focused on in class a lot. Okay, there are many things, many problems I focused on. Those are, I repeat them for a reason. Okay, not just because I like repetition, but problems in the homework also you should do them. You should see that I could twist a bit. So for the ring proofs, I said you can expect one proof from characteristic and one from the first 4 lectures, right? So what from the first, how many theorems did we do? We did this one today here. Then we did that if R is a field, if R is a finite integral domain, then R is a field. If R is a commutative ring, then R is a field if and only if it has only 2 ideals. If R is a finite commutative ring and A is not a unit, then A is a 0 divisor. A is not 0, of course. What as well? A field is an integral domain. If R is a 0, if 1 is equal to 0 in R, then R is a 0 ring. So these are the proofs you should expect. Even if the Sylow 3 entire proof is S again, you will see tomorrow. Okay, it's in 12 hours. So, but again, don't. It's gonna be easier than this one. It's gonna be shorter. If we're gonna prove Sylow theorem, please wink. I'm opening my eyes, so I don't know. The first one you're not gonna have to prove. So for the first one, I can wink that you won't have to prove it. I mean, this is a common info by now, I guess. The first one you won't have to prove it. Possible to have questions from yes. It's possible to have, or it's possible not to have. Like you could have some questions from here on that, or it's possible that you don't have. We don't need homomorphism. Nope. 2 and 3 you don't need. Pardon me. Homomorphism theorem 2 and 3. First second and third isomorphism theorem. Sorry. Since 103 is prime, it has degree 2. It can be written. Which one? Oh, find the field of order 103 squared. So 103 is congruent to 3 mod 4. So x squared plus 1 is reducible in F103. Okay, that's from the midterm. And so you could have 103x modulo x squared plus 1 is reducible. I don't know about x squared plus 2. I mean, I can easily check it, but it's yeah, it's a different criteria. Okay. So people, questions? Okay, can I turn this? Okay, well, we need to use Fermat's theorem in some of the proofs. Well, we need to use Fermat's theorem in the, I don't know. I can't remember. Maybe yes, maybe no. Maybe yes, maybe no. I really can't remember. I really can't remember. Can you show that if A is a subgroup, then 5A is a subgroup? This you could do by just by the definition. Okay, so let A, B be in phi of A. Okay, so I'll take the questions from people that are here. You have questions? You have questions? Okay. So can you show if A is a subgroup of G, then phi of A is a subgroup of H? I think, did I show it in the written notes? Go under lecture by lecture and course outline. And I have written notes. Can you please check these? I think it might be shown there. On the lecture by isomorphism, there was a part where the recording messed up. And then I rewrote everything by notes. Okay. Great. Is it possible to show that XP is irreducible by showing that the quotient is a field? You might be able to do that, but I don't know if you can do it. I don't know if you can show that without showing it's irreducible. But maybe you could. Who knows? Where is the solution of homework 9? Homework 9 has been recorded. The solutions to homework 9 have been recorded before you hand them in. 1 or 2 questions, right? One of them is the S4 question. Okay, and the others you won't have to worry about. Okay. Great. So I mean, worry about the parts that I did in homework 9. Okay, worry about the parts that I did in homework 9, homework 8, and even homework 9. The important parts also, there is a student who was kind enough to post her handwritten notes as well, right? So these are the important parts. If there's a question that I didn't do, that mostly involves Sylow subgroups. So you're not going to have that tomorrow. You're not going to have any question on Sylow subgroups except possibly proving the second or the third Sylow theorems and stating the 3 of them. Okay, great. I'll shut this. Last call for questions. Last call for questions. Did we cover? Yes, we covered all the questions in practice ring yesterday and before yesterday. Is that right? We covered all of them? Almost. Well, the practice ring questions. We went through all of them. Yes, so yesterday and before yesterday. Okay, everybody. See you, John. See you. Relax, and if you studied, it's going to be okay. Trust me. it's going to be easier than this. It's going to be easier than this. Thank you. Thank you. Merry Christmas to you too. Thank you. Will you round? Oh man, I don't know. I don't know if I'll round up. Now, let's write the final first and then we see. Okay. I'll leave you all. I wish you good luck. It has been a pleasure teaching you all. I hope you enjoyed the class. I know it was a challenging class, but you guys have all the tools to do well. And yeah, even though you might not think it, but you do. Okay. Great. Thank you. Thank you. Okay. Great. Bye-bye. Oh yeah, and how do I write? And yeah.